Isaac Newton constructed one of the most radical intellectual systems in human history. Born in 1642, he lived through the collapse of Aristotelian philosophy. The old certainties were crumbling as new methods of investigating nature emerged across Europe. Newton stood at this crossroads and helped forge a new path forward. Most people know Newton for his laws of motion and universal gravitation. They imagine him as a pure scientist devoted only to mathematics and physics. This image is a distortion that arose during the Enlightenment, when thinkers stripped away uncomfortable truths. The real Newton spent more time on theology and alchemy than on physics. He wrote over 1 million words on alchemy and 3 million on theology and biblical prophecy. These were not hobbies disconnected from his scientific work. For Newton, natural philosophy, theology, and the study of ancient wisdom formed a unified whole. He saw himself recovering truths that the ancients knew, but that had been corrupted over time. His religious beliefs were heretical by the standards of his day and remained hidden throughout his life. He denied the Trinity, considered Orthodox Christianity a corruption, and believed God acts directly in the physical world. Newton also developed a distinctive methodology that bridged two opposing camps. Continental rationalists like Descartes trusted pure reason to reveal truths about nature. British empiricists emphasized sensory experience as the foundation of knowledge. Newton refused to choose between these approaches. He insisted that fundamental concepts like space and extension come from the intellect. Yet he demanded that laws of nature must be derived from careful observation and experiment. This methodological synthesis became enormously influential. Every major Enlightenment thinker, from Locke to Kant, grappled with Newton's ideas. David Hume explicitly modelled his philosophical method on Newton's approach to natural philosophy. Immanuel Kant developed his critical philosophy partly to resolve tensions Newton's work had created. Understanding Newton requires examining both what he revealed publicly and what he concealed. His published works present mathematical demonstrations and experimental results with minimal philosophical commentary. His private manuscripts reveal a man obsessed with decoding biblical prophecy and alchemical texts. Both dimensions shaped his approach to investigating nature. Part 1. The Philosophical Foundation. Newton entered Cambridge University in 1661 when intellectual combat raged across Europe. Cartesianism was spreading rapidly, challenging both Aristotelian scholasticism and emerging experimental approaches. René Descartes had argued that the physical world operates like a vast machine governed by mechanical laws. He rejected action at a distance and insisted that matter could only affect neighbouring matter through direct contact. Descartes believed space was nothing more than the extension of bodies filling it completely. His universe contained no void, only matter pushing against other matter in vast whirlpools called vortices. This mechanical philosophy appealed to many because it seemed to eliminate mysterious or occult forces from nature. But it troubled others who saw it reducing God's role to merely starting the cosmic machine. Newton encountered these debates early, and they shaped his entire intellectual development. He read Descartes intensively, but ultimately rejected nearly every major Cartesian doctrine. This rejection was not casual disagreement, but fundamental opposition extending to basic metaphysics. Where Descartes identified matter with extension, Newton insisted space exists independently of any material bodies. Newton's conception of absolute space became central to his entire system. He argued that space is not defined by relations between objects as Descartes claimed. Instead, space is a real thing existing on its own, whether any matter occupies it or not. This was radical because it made space into something almost divine in nature. Newton went further and identified space with God's presence throughout creation. In the General Scholium added to the Principia's second edition, he wrote that God exists everywhere and always. By existing everywhere, God literally constitutes space itself through his eternal omnipresence. This was shocking to Cartesians and Leibnizians, who thought God existed beyond or outside the physical world. For Newton, saying God exists outside space was equivalent to saying God does not exist at all. Every entity must connect with space in some way, or it simply has no reality. This applied to minds, souls, and God himself just as much as to physical bodies. The idea horrified many contemporaries who saw it as blasphemously materializing the divine. Newton also rejected the Cartesian view of motion as merely relative to surrounding bodies. Descartes had argued that motion is just a body's changing relations with its immediate neighbours. This meant there was no fact about whether something truly moved or remained at rest. Everything depended on which frame of reference you adopted. Newton insisted this made physics impossible because it eliminated any stable foundation for laws of motion. He needed absolute motion and absolute space to formulate his dynamics properly. His famous rotating bucket experiment attempted to demonstrate that true rotation could be distinguished from mere apparent rotation. When water in a spinning bucket climbs up the sides, Newton argued, this reveals genuine rotation relative to space itself. Yet Newton faced a profound problem that he never fully resolved. Absolute space and time cannot be observed or measured directly in any experiment. We only ever experience relative motions and relative positions of observable bodies. Newton acknowledged this explicitly, noting that we lack direct empirical access to absolute quantities. His solution was to treat absolute space as a conceptual foundation, enabling physics to proceed. We use theory-mediated measurements to infer properties we cannot observe directly. Forces impressed upon bodies provide the key to distinguishing real from apparent accelerations. True motion is neither generated nor changed, except by forces acting on the body itself. This created tensions that subsequent philosophers spent centuries trying to resolve. Newton claimed to be following experimental philosophy and deriving conclusions from phenomena alone. Yet his fundamental framework relied on metaphysical entities beyond all possible observation. Critics charged that he smuggled in precisely the kind of speculation he claimed to reject. The dispute with Gottfried Leibniz brought these issues to public attention. Leibniz developed relationalism, the view that space is nothing but relations among physical objects. Time, likewise, is nothing over and above the succession of events involving those objects. For Leibniz, absolute space was an incoherent notion that violated the principle of sufficient reason. Samuel Clarke defended Newton in a famous correspondence with Leibniz during 1715 and 1716. The debate ranged across physics, metaphysics, and theology, with neither side conceding ground. Both sides recognized that fundamental questions about God's relation to creation were at stake. This was not merely abstract philosophy, but touched the deepest questions about divine action. Newton believed God actively intervenes in the universe to maintain its order and structure. He rejected Leibniz's claim that God created a perfect world, requiring no subsequent divine adjustment. For Newton, signs of divine governance appeared everywhere in phenomena requiring continuous providential activity. The solar system's stability and the arrangement of planetary orbits both suggested ongoing intelligent direction. This theological dimension was inseparable from Newton's natural philosophy despite later sanitization. The general scholium concluded with Newton declaring that discussing God from phenomena is natural philosophy's proper task. This was not an afterthought, but expressed his core conviction about physics and theology's unity. He was doing theology when he calculated planetary orbits just as much as when studying biblical prophecy. Part 2. The Methodology Revolution. Newton developed his methodological approach through decades of bitter intellectual combat. His first major publication in 1672, on light and colour, sparked immediate controversy. Robert Hooke, Christian Huygens, and others attacked both his experimental claims and theoretical interpretations. Newton felt profoundly misunderstood, and this experience shaped his lifelong aversion to public debate. The attacks forced Newton to articulate meta-level principles about how natural philosophy should proceed. He needed to distinguish what he considered rigorous knowledge from mere speculation or hypothesis. This led him to develop what scholars now call his epistemic triad. He distinguished theories that are certain and experimentally confirmed from hypotheses that remain speculative. Queries formed the third category. Propositions uncertain but providing proper means to establish theoretical certainty. Hypotheses could play a supporting role in investigations without being claimed as established truth. Newton temporarily assumed hypotheses as helping premises in reasoning from phenomena to conclusions, but he refused to present them as demonstrated facts derived from observation. This framework evolved substantially between the Principia's first edition in 1687 and later versions. The first edition of Book 3 contained 9 propositions labelled as hypotheses. By the second edition in 1713, Newton restructured everything and retained only 2 hypotheses. The others were relabelled as rules of reasoning or phenomena, depending on their logical function. The 4 rules of reasoning became Newton's most explicit methodological statement. Rule 1 demands admitting only causes that are both true and sufficient to explain appearances. This is Newton's version of Occam's razor, his principle of parsimony in theory construction. More is vain when less will serve as adequate explanation. Rule 2 states that similar natural effects must be assigned the same causes as far as possible. The fall of stones in Europe and America share the same cause as does respiration in humans and animals. This rule licenses extending conclusions from observed cases to unobserved similar cases. It provides the bridge from particular experiments to universal natural laws. Rule 3 asserts that qualities found universal in all bodies within experimental reach are universal properties. If every body we can test proves impenetrable, we conclude all bodies possess impenetrability. This rule justified treating gravity as a universal property of all matter everywhere. Newton had only tested terrestrial objects and celestial bodies visible from Earth. Rule 4 became the most controversial and philosophically rich of Newton's methodological principles. Propositions gathered from phenomena by induction should be regarded as exactly or very nearly true. They maintain this status until contrary phenomena appear that modify them or specify exceptions. This rule explicitly prioritizes propositions over hypotheses and experiment over speculation. The rule's key insight is that inductive propositions retain tentative certainty despite being potentially revisable. Newton recognized that perfect certainty lies beyond reach in natural philosophy. Yet he insisted we can achieve knowledge sufficient for practical and theoretical purposes. We should not let hypothetical possibilities nullify conclusions properly drawn from phenomena. To the second edition, Newton added the general scholium, containing his most famous methodological declaration. After explaining that he could not deduce gravity's cause from phenomena, he wrote hypotheses non fingo. This Latin phrase means either I frame no hypotheses or I feign no hypotheses. The ambiguity proved fertile ground for centuries of scholarly debate. Newton clarified that whatever is not deduced from phenomena must be called a hypothesis. Such hypotheses have no place in experimental philosophy, whether metaphysical, physical, mechanical, or based on occult qualities. In experimental philosophy, particular propositions are inferred from phenomena, then rendered general by induction. This marked Newton's mature statement, distinguishing his method from rationalist system building. The phrase was directed primarily against Descartes and Leibniz, who proposed mechanical explanations for gravity. Leibniz introduced whirlpools or vortices as hypothetical fluids surrounding planets to account for orbital motion. Newton considered this feigning hypotheses, inventing unobservable mechanisms not required by observational evidence. He had established gravity's mathematical law, and that sufficed for explaining celestial phenomena. Critics charged that Newton himself feigned hypotheses by postulating action at a distance. How could one body affect another across empty space without any intervening medium or mechanism? This seemed to reintroduce occult qualities that mechanical philosophy had supposedly eliminated from nature. Leibniz and continental thinkers found it philosophically repugnant, despite its mathematical success. Newton's response was that he had demonstrated gravity exists and acts according to precise mathematical laws. Whether gravity operates through unknown mechanisms or directly across space remained an open question. He privately believed some mechanism might exist, and even speculated about ethers at various times. But he refused to publish such speculations as demonstrated truths derived from phenomena. This methodological stance represented a profound shift in what counted as legitimate scientific explanation. Previous natural philosophy demanded identifying causes and mechanisms underlying all observed effects. Newton argued that mathematical description of how phenomena behave could constitute adequate knowledge. We need not know why gravity follows an inverse square law to use that law successfully. The distinction between knowing that and knowing why became central to subsequent philosophy of science. Newton showed that precise mathematical laws describing observable regularities constitute real scientific achievement. Demanding mechanical explanations or underlying causes might be premature before sufficient phenomena are examined. Better to establish secure mathematical descriptions than to multiply unsupported hypothetical mechanisms. Yet Newton never abandoned the search for deeper explanations or underlying physical causes. His optics concluded with dozens of queries posing questions about the nature of light, matter, and force. These queries were clearly not demonstrated conclusions, but speculative proposals for future investigation. They suggested subtle fluids, active principles, and mechanisms that might explain observed phenomena. The methodology balanced two opposing dangers that Newton navigated throughout his career. Pure empiricism risked drowning in observations without achieving general understanding or theoretical power. Pure rationalism risked constructing elegant systems detached from observational constraints and experimental test. Newton's synthesis demanded mathematical rigor and deductive reasoning disciplined by empirical phenomena. His approach required extraordinary mathematical invention to handle the complexities of real observations. The Principia uses sophisticated geometric methods to derive conclusions from idealized situations. Then it shows how to account for deviations between ideal theory and actual measurements. Successive approximations increase model complexity to capture phenomena with greater accuracy. This iterative method of refinement became standard practice in mathematical physics. You start with simplified models, capturing essential features while ignoring complicating factors. After securing basic understanding, you systematically add complications and correct for disturbing influences. Newton demonstrated this approach throughout the Principia's development of celestial mechanics. The methodology also incorporated what we would now call error analysis and uncertainty quantification. Newton explicitly acknowledged that measurements contain errors and observations capture only approximations. He developed techniques for extracting reliable conclusions from imperfect data. This recognition that certainty comes in degrees marked a mature understanding of empirical science. Newton's rules of reasoning influenced methodology for 2 centuries after his death. They shaped how scientists justified inductive inferences and extended conclusions beyond observed cases. David Hume's skeptical analysis of causation and induction took Newton's approach as its target. Immanuel Kant developed transcendental philosophy partly to explain how Newtonian science achieves synthetic knowledge. The hypotheses non fingo declaration became a rallying cry for empiricist philosophy of science. 19th-century positivists invoked Newton as their patron saint, rejecting metaphysical speculation. This was deeply ironic, given Newton's private commitment to metaphysics, theology, and alchemy. The sanitized Newton of Enlightenment mythology bore little resemblance to the actual historical figure. Part 3. The Hidden Theology. Isaac Newton was a heretic who concealed his true beliefs throughout his entire adult life. He rejected the doctrine of the Trinity, the central dogma of institutional Christianity. He believed Orthodox Trinitarianism represented a catastrophic corruption of original Christianity. This corruption occurred during the 4th century following the Council of Nicaea in 325. Newton's theological investigations were as intensive and original as his work in mathematics. He wrote treatises on biblical prophecy totaling over 3 million words. He studied ancient manuscripts, compared textual variants, and traced the evolution of Christian doctrine. His textual scholarship was rigorous and systematic, applying critical methods to sacred texts. The manuscript he sent to John Locke disputing the Trinity's scriptural basis was never published. Newton feared the consequences of revealing views that would be considered formally heretical. In 17th century England, heresy could destroy careers and potentially endanger lives. Cambridge professors were required to take holy orders in the Church of England. Newton faced a crisis in 1675 when he should have been ordained. He could not, in conscience, swear to articles of faith he believed fundamentally false. Isaac Barrow, his patron and predecessor as Lucasian professor, helped him obtain special dispensation. The statute requiring ordination was changed specifically to exempt the Lucasian chair. This narrow escape convinced Newton that his theological views must remain absolutely private. He adopted what scholars call Nicodemism, concealing heretical beliefs through outward conformity. He attended church regularly and subscribed publicly to Anglican articles when taking government office. But these were strategic concessions protecting his ability to continue his work. Newton's heresy centered on his conviction that God is absolutely one, not 3 persons in one substance. Christ was the Son of God and the Messiah, but not co-equal or co-eternal with the Father. This made Newton an Arian, following the ancient theologian Arius, whose views Nicaea had condemned. Only the Father is the supreme God, existing from eternity and possessing ultimate divine authority. Newton's reasoning combined scriptural analysis with philosophical argument about the nature of divinity. He found no clear scriptural basis for Trinitarian formulas in the earliest manuscripts. Later additions to texts appeared designed to support doctrines developed centuries after Christ. The famous Johannine comma in 1 John was a late interpolation absent from ancient sources. He also argued that the Trinity involved logical contradictions and philosophical incoherence. How could 3 distinct persons share one substance while remaining genuinely distinct? The Father sends the Son, yet they are equally eternal and necessary. These paradoxes suggested human corruption of simple original truths rather than divine mystery. Newton believed early Christians worshipped one God the Father and honored Jesus as his appointed Messiah. The elaborate Trinitarian metaphysics emerged from Greek philosophical influence, corrupting Hebrew monotheism. Athanasius and his followers imposed this corruption through political maneuvering and textual manipulation. Newton's massive manuscript attacking Athanasius detailed this alleged historical process. This theological framework connected directly to Newton's natural philosophy in multiple ways. His absolute space and time replicated in physics his conception of God's absolute unity. Just as God is one and indivisible, so space and time are unified and cannot be decomposed into relations. The failure to distinguish absolute from relative in physics mirrors theological errors about God's nature. Newton explicitly stated that God's omnipresence literally constitutes space through his eternal existence everywhere. Duration and space are modes of God's existence, not independent containers. This made space something closer to divine than to material reality. It explains why Newton insisted everything, including minds and souls, must relate to space somehow. His conception of divine action in the world also shaped his physics fundamentally. Newton believed God actively maintains the universe's order through continuous providential intervention. The solar system's stability requires occasional divine adjustments to prevent accumulating perturbations. Gravity itself might be the direct action of God's will, rather than a mechanical push. This contrasted sharply with the deist view becoming popular among some Enlightenment thinkers. Deists imagined God creating the universe, then letting it run like a perfect machine. Newton found this notion theologically objectionable and physically implausible. The evidence suggested ongoing divine governance, not a self-sufficient mechanical system. Newton also pursued what he called the Prisca Theologia, the ancient theology. He believed that God revealed true religion to Noah and the patriarchs before Moses. This original religion consisted of worshipping the one true God and following two simple moral commands. Love God completely and love your neighbor as yourself. All ancient peoples originally shared this pure religion, according to Newton's reconstruction. The priesthoods of Egypt, Babylon, and Greece possessed corrupted fragments of original revelation. Pythagoras learned true wisdom during his travels and taught it to disciples in symbolic form. Ancient temples were designed as models of the heliocentric cosmos, expressing cosmological truth. This theory allowed Newton to see his own work as recovering ancient wisdom. He was not discovering new truths, but rediscovering what ancient sages had known. The heliocentric system, mathematical laws of nature, and proper worship of God formed a unified whole. Modern philosophy had declined from ancient heights, and Newton aimed to restore lost knowledge. Newton studied alchemy partly as an attempt to decode ancient wisdom transmitted in symbolic language. Alchemical texts might preserve truths about matter and force disguised in allegory. The philosopher's stone could be both a literal substance and a symbol of deeper understanding. This was not irrational mysticism, but a coherent interpretive framework for studying ancient sources. His biblical chronology attempted to establish accurate dating for ancient history using astronomical calculations. He analyzed references to celestial events in ancient texts to reconstruct true chronology. This combined his astronomical knowledge with textual scholarship in service of theological understanding. For Newton, these were not separate enterprises, but aspects of one unified investigation. Newton's study of biblical prophecy aimed to decode God's plan for human history. The books of Daniel and Revelation contained encrypted information about past and future events. He developed elaborate interpretive principles for matching prophetic symbols to historical realities. The prophecies confirmed that the Trinitarian corruption would persist until the end times. He calculated that the restoration of true religion would not occur until approximately 2060. This date came from applying the day-year principle to prophetic timelines in Daniel. The calculation assumed the corruption began when Charlemagne was crowned Holy Roman Emperor in 800. Newton saw himself living in the midst of the long prophesied apostasy. The emotional energy Newton invested in theological research was as intense as his scientific work. These were not casual hobbies pursued in spare moments between real investigations. Theology and natural philosophy competed for his attention throughout his career. Both aimed at understanding God's nature and revealing divine truth to humanity. After Newton's death, his theological manuscripts created a dilemma for his executors. Publishing them would expose the great Newton as a heretic and damage his reputation. Suppressing them meant hiding a major dimension of his intellectual life and motivations. They chose suppression, and the manuscripts remained largely unknown until the 20th century. When Newton's theological views finally became public knowledge, scholars struggled to integrate them. How could the founder of modern science hold such apparently irrational religious beliefs? This revealed modern assumptions about science and religion needing to be separate and opposed. For Newton, they form parts of a seamless quest for truth about God and creation. Part 4. The Optical Wars. Newton bought his first glass prism in 1666 while still a student. He began experimenting with light and colour in ways that would revolutionize optics. His discoveries challenged prevailing theories about light's nature and generated decades of bitter controversy. These disputes shaped both his scientific method and his approach to intellectual combat. The standard view held that white light is pure and simple, while colours represent corruptions or modifications. When light passes through glass, the material somehow alters pristine white light to produce colours. The colour spectrum seen through prisms resulted from the glass degrading or corrupting the light. This meant that passing light through more glass should increase the corruption. Newton's experiments demolished this theory with elegant simplicity. He passed white sunlight through one prism, which separated it into the familiar rainbow spectrum. Then he passed the coloured spectrum through a second prism, positioned to reverse the effect. The separated colours recombined perfectly into white light again, without any corruption. This proved that colours are not corruptions of white light, but rather white light's constituents. White light is composite, a mixture of different coloured rays that normally travel together. The prism does not create colours by modifying light, but merely separates pre-existing components. Different colours correspond to light rays with different degrees of refrangibility through glass. Newton concluded that light itself comes in different varieties, corresponding to different colours. Red light differs fundamentally from blue light in properties determining how materials refract it. Each colour has a characteristic angle of refraction when passing from air into glass. The spectrum shows this spread of refraction angles for white light's component rays. He presented these findings in his first major publication to the Royal Society in 1672. The paper was titled Letter Containing His New Theory About Light and Colours. Newton claimed his experiments provided certain demonstrations, not mere hypothetical speculation. He insisted the results followed with geometric necessity from experimental phenomena. Robert Hooke immediately attacked Newton's paper with multiple objections and alternative explanations. Hooke was England's leading authority on optics and resented the younger Newton's challenge. He claimed Newton's theory depended on assuming light consists of particles or corpuscles. Since Hooke believed light travels as waves, Newton's entire theory must be mistaken. This criticism infuriated Newton because he felt Hooke completely misunderstood the paper's argument. Newton insisted his colour theory did not depend on any hypothesis about light's ultimate nature. Whether light consists of particles or waves, the experimental facts about refrangibility remain unchanged. The theory was a demonstrated conclusion, not a speculative huygens. Christian Huygens also criticized Newton's conclusions, though in more measured terms than Hooke. Huygens had developed a sophisticated wave theory of light building on earlier ideas. He showed that treating light as waves propagating through an ether could explain reflection and refraction. His principles stated that each point on a wavefront generates new wavelets spreading spherically. The debate over whether light consists of particles or waves would persist for over 2 centuries. Newton developed and defended the corpuscular theory, while Hooke and Huygens championed wave theories. Each side could explain some phenomena convincingly while struggling with others. The particle theory handled straight-line propagation and sharp shadows naturally. Newton argued that if light were waves, it should diffract around obstacles like sound does. We hear sounds from around corners but cannot see light sources blocked by obstacles. This suggested light travels in straight lines like particles rather than spreading in all directions like waves. Later, evidence of light diffraction through narrow slits would challenge this argument. The corpuscular theory explained reflection as particles bouncing off smooth surfaces elastically. Different sized or shaped corpuscles could account for different colours, having different refractive properties. Refraction occurred when corpuscles accelerated entering denser media, bending their trajectories toward the normal. This required light travelling faster in denser media, a prediction later proved wrong. Newton acknowledged certain phenomena that seemed to require wave-like explanations. Thin films like soap bubbles display coloured interference patterns depending on film thickness. Light sometimes reflects and sometimes transmits through the same film with no obvious difference in conditions. Newton proposed that corpuscles possess fits, alternately disposing them toward reflection or transmission. He suggested corpuscles might create waves in the ether as they travel. These waves could overtake the corpuscles and induce the periodic fits of reflection and transmission. This hybrid theory tried to preserve corpuscular foundations while incorporating wave-like elements. It showed Newton's willingness to modify his theory when phenomena demanded it. The Optics, published in 1704, became Newton's comprehensive statement on light. Unlike the mathematical Principia, it was written in English and accessible to wider audiences. The book detailed experiments readers could replicate and built conclusions carefully from observations. It included extended queries, posing questions and suggesting explanations for further investigation. Newton used the queries to speculate more freely than the Principia's austere style permitted. He asked whether light corpuscles might have different sizes, corresponding to different colours. He wondered whether ethereal mediums with varying densities could explain optical phenomena. These were clearly not demonstrated conclusions, but proposals for future natural philosophy. The optics influenced subsequent science differently than the Principia, despite its less mathematical character. It provided a model for experimental investigation, combining careful observation with theoretical interpretation. The queries showed how to pose productive questions, guiding research without premature dogmatic claims. David Hume explicitly modelled his philosophical method on the optics approach. The controversy with Hooke left lasting scars on Newton's personality and scholarly practice. He came to dread intellectual debate and delayed publishing major works for decades. The optics waited until after Hooke's death in 1703 to appear in print. Newton's aversion to controversy meant potentially valuable ideas remained private throughout his life. Thomas Young's double-slit experiment in 1801 provided powerful evidence for wave theory. When light passes through two narrow slits, it creates interference patterns on a screen. Bright and dark bands appear in regions where waves from both slits reinforce or cancel. This behavior could not be explained by corpuscles traveling in straight lines. Throughout the 19th century, additional experiments on interference, diffraction, and polarization supported wave theory. Jean-Baptiste Biot initially explained polarization using particle theory, but later evidence favored waves. By century's end, the wave theory dominated physics, and Newton's corpuscular approach seemed refuted. Then, quantum mechanics revealed that both perspectives capture partial truth about light's dual nature. The photoelectric effect, discovered in the early 20th century, revived particle concepts unexpectedly. Light ejects electrons from metal surfaces in ways that wave theory cannot explain properly. Einstein proposed that light consists of discrete packets of energy, now called photons. The photon model made light both particle and wave, depending on experimental context. Modern physics recognizes wave-particle duality as fundamental to quantum mechanics. Light exhibits wave behavior in interference and diffraction experiments. It exhibits particle behavior in photoelectric effect and Compton scattering experiments. Neither classical waves nor classical particles adequately describe quantum entities. Newton's corpuscular theory thus anticipated aspects of modern photon theory despite being incomplete. His intuition that light involves discrete entities travelling through space captured partial truth. The debate between Newton and Huygens could not be resolved within classical physics. Both were right and both were wrong in ways neither could imagine. Part 5. The Principia and Universal Mathematics. The Mathematical Principles of Natural Philosophy, published in 1687, became the most influential scientific work ever written. Newton presented a mathematical system unifying terrestrial and celestial mechanics under common laws. He showed that the same force causing apples to fall makes planets orbit the sun. This unification represented a stunning intellectual achievement, transforming natural philosophy's scope and methods. The work's origins lie in correspondence with Robert Hooke during 1679 and 80. Hooke claimed to have discovered that planetary motion results from two component forces. A tangential motion continues by inertia while central force pulls the planet toward the Sun. The orbit results from combining these two motions according to precise mathematical laws. Hooke proposed that the central force decreases with the inverse square of distance from the Sun. This inverse square law matched what Christopher Wren and Edmund Halley also suspected. But none of them could derive Kepler's empirical laws of planetary motion from this force law. The mathematical demonstration required techniques and insights they lacked. Newton had actually worked out much of this mathematics years earlier, but had not published it. In 1684, Halley visited Newton and asked whether inverse square force produces elliptical orbits. Newton replied immediately that it does, and that he had calculated this already. He could not find his earlier papers, but promised to work through the demonstration again. This query sparked Newton's most intensive creative period, producing the Principia in under 2 years. The project expanded far beyond the original question into a comprehensive mathematical treatment of motion. Book 1 develops general theorems about motion under central forces using geometric methods. Book 2 analyzes motion through resisting media and critiques Cartesian vortex theories. Book 3 applies the mathematics to our actual solar system, deriving planetary motions from empirical data. This was the truly revolutionary achievement, linking abstract mathematics to observed celestial phenomena. Newton showed how to infer universal gravitation's existence and mathematical form from Kepler's laws. He then predicted corrections to Kepler's idealizations from planets' mutual gravitational interactions. The Principia opens with definitions of fundamental concepts like mass, momentum, and force. These definitions gave precise mathematical meanings to terms previously used ambiguously in natural philosophy. The famous scholium on absolute space and time follows, establishing Newton's metaphysical foundations. Then come the 3 laws of motion, forming the logical basis for all subsequent arguments. Newton's first law states that bodies persist in rest or uniform motion unless forces act upon them. This principle of inertia was not original to Newton, but derived from Descartes and Galileo. However, Newton made it foundational and gave it precise mathematical formulation. Inertia explains why planets continue moving without perpetually requiring force to sustain motion. The second law states that change of motion is proportional to impressed force and occurs in that force's direction. This gave the crucial quantitative connection between force and resulting acceleration. Modern physics writes this as force equals mass times acceleration. Newton expressed it geometrically in terms of momentum changes over infinitesimal time intervals. The third law declares that every action has an equal and opposite reaction. When one body exerts force on another, the second exerts equal force back on the first. This was Newton's original contribution among the 3 laws and proved essential for complex systems. It ensures that internal forces within a system cancel, preserving total momentum. From these foundations, Newton derived a vast array of theorems using geometric methods. He proved that inverse square central force produces elliptical orbits with force center at one focus. He showed how orbital period relates to distance following Kepler's third law exactly. These results vindicated Kepler's empirical laws by deriving them from fundamental principles. Book 3, titled The System of the World, applied abstract mathematics to real astronomical observations. Newton began with 6 phenomena describing regularities in planetary and lunar motions. Then he applied his rules of reasoning to infer universal gravitation from these observed patterns. The argument combined rigorous mathematics with careful attention to empirical constraints. Newton showed that the Moon's centripetal acceleration equals the gravitational acceleration at Earth's surface. When he calculated the force needed to maintain the Moon's orbit, it matched terrestrial gravity. This verified that the same force operates on Earth and in the heavens. The ancient distinction between terrestrial and celestial realms collapsed into one unified physics. He then demonstrated that all planets and their satellites obey the same inverse square law. Jupiter's moons, Saturn's moons, and the Sun's planets all follow identical mathematical patterns. This universality suggested one force pervading all space, governing all celestial motions. Newton called this force gravitation and showed it acts proportional to masses involved. The mathematical form was that force equals the product of masses divided by distance squared. This gave a precise quantitative law, replacing qualitative explanations of planetary motion. Every particle of matter attracts every other particle with this mathematical force law. The implications were staggering, suggesting fundamental unity underlying all physical phenomena. Newton's method involved idealizing complex situations, then systematically adding complications. He first solved motion of two bodies interacting through gravity alone. Then he added perturbations from third bodies and corrections for non-spherical mass distributions. Each step increased agreement between theoretical predictions and actual observations. He calculated corrections to the Moon's motion from the Sun's perturbing influence. He explained the precession of Earth's axis from tidal forces on the equatorial bulge. He showed how Jupiter and Saturn's mutual gravitational pulls perturb their orbits slightly. These corrections demonstrated how to extract precise predictions from messy real-world phenomena. The Principia also derived the tides from gravitational theory with stunning success. Ocean tides result from the Moon and Sun's differential gravitational forces on Earth. Newton calculated how tide heights depend on lunar and solar positions throughout their cycles. The mathematical predictions matched observed tidal patterns in impressive detail. Yet Newton acknowledged fundamental limitations in his gravitational theory's explanatory completeness. He had established that gravity exists and acts according to precise mathematical laws. But he could not explain how gravity operates or what mechanism transmits force across empty space. Action at a distance without physical contact seemed philosophically problematic or even occult. Critics, especially on the continent, attacked this aspect as abandoning mechanical philosophy's standards. Descartes and Leibniz insisted that matter affects other matter only through direct physical contact. Gravitational attraction across vacuum violated this mechanical principle, returning to Aristotelian occult qualities. Newton's followers struggled to defend against these philosophical objections. Newton's response was that mathematical description of how gravity operates suffices for natural philosophy. It is enough that gravity really exists and acts according to discovered laws. These laws explain and predict an enormous range of phenomena with quantitative precision. Demanding mechanical explanations might be premature before fully exploring mathematical consequences. He hinted that gravity might result from differential ether pressure or other physical mechanisms, but he refused to publish mere speculations as demonstrated truths. Hypotheses non fingo meant not feigning explanatory mechanisms unsupported by experimental evidence. The mathematical force law had secure empirical foundation, while mechanical explanations remained uncertain. The Principia created mathematical physics as a distinct discipline with its own standards and methods. Previous natural philosophy had been either qualitative speculation or geometric demonstration from axioms. Newton showed how to construct mathematical theories constrained by empirical phenomena and tested through predictions. This methodology became the model for all subsequent exact science. The work's influence extended far beyond physics into philosophy and intellectual culture generally. It provided concrete demonstration that human reason could penetrate nature's deepest secrets. The Enlightenment's confidence in reason's power drew heavily on Newton's spectacular success. Thinkers across disciplines sought to become the Newton of their field. Part 6. The Alchemical Pursuit. Isaac Newton wrote over 1 million words on alchemy and chemical processes. These were not casual notes, but intensive systematic investigations spanning decades of his career. He copied alchemical texts laboriously by hand, conducted dangerous experiments in his laboratory, and developed theories about matter's active principles. For Newton, alchemy was as legitimate an investigation as optics or mathematics. The modern separation between chemistry and alchemy did not exist in Newton's time. Both investigated matter's properties and transformations through observation and experiment. Alchemy included metallurgy, medicine, dye-making, and other practical chemical arts. It also pursued more speculative goals like transmuting base metals into gold. Newton's alchemical investigations aimed to understand the forces operating at matter's smallest scales. He believed that subtle interactions between particles might involve short-range, attractive and repulsive forces. These micro-level forces could explain chemical reactions, phase changes and material properties. Alchemy provided experimental evidence about matter's behavior that mechanical philosophy could not explain. Mechanical philosophers like Descartes tried to explain all phenomena through matter's size, shape, and motion alone. Particles collide and interlock mechanically like machine parts fitting together. But this framework struggled to account for chemical affinities where certain substances combine preferentially. Why does acid dissolve some metals but not others, despite similar mechanical properties? Newton suspected that active principles beyond mere mechanical interactions governed chemical phenomena. Particles might attract or repel each other through forces analogous to gravity, but operating at different scales. These forces could explain selective chemical combination and other phenomena resisting mechanical explanation. Alchemical experiments potentially revealed clues about these hidden forces. His manuscript of Natures. Obvious laws and processes in vegetation analyzed plant growth using alchemical concepts. He proposed that active principles draw appropriate particles from soil and air into growing structures. These selective attractions explained why plants incorporate certain elements while excluding others. The process resembled chemical reactions where specific substances combine according to intrinsic affinities. Newton also pursued the philosopher's stone, the legendary substance allegedly enabling transmutation and conferring wisdom. This was not irrational superstition, but a coherent research program within the period's framework. If forces operating between particles determined chemical properties, changing those forces could transform substances fundamentally. The philosopher's stone might be a material catalyst, triggering systematic changes in metallic composition. Alchemical texts frequently used allegorical and symbolic language, protecting secrets from uninitiated readers. Newton spent enormous effort decoding these symbols to extract practical chemical knowledge. He believed ancient alchemists possessed genuine understanding transmitted through deliberately obscure terminology. This connected to his broader Prisca Theologia project, recovering ancient wisdom. The secrecy pervading alchemy aligned with Newton's own preference for concealing important ideas. He kept his alchemical work entirely private throughout his life. After his death, executors found a laboratory full of chemical apparatus and notebooks filled with experiments. These revealed an intensive practical program complementing his mathematical natural philosophy. Newton's interest in active principles connected his alchemy to his physics in fundamental ways. Gravity itself might be an active principle rather than purely mechanical collision. Matter might possess inherent tendencies towards certain motions beyond mere inertia. These ideas contradicted mechanical philosophy's program of explaining everything through passive matter and contact forces. The final query, added to later optics editions, expressed these speculations most clearly. Newton asked whether particles of matter possess forces enabling them to attract at small distances. These short-range forces could explain chemical reactions, surface tension, capillary action, and other phenomena. The hierarchy of forces at different scales unified chemistry and physics under common principles. He suggested that nature operates through mutual attractions and repulsions among smallest particles. These forces vary with distance following mathematical laws, perhaps analogous to gravity. Chemical affinity, heat, electricity and magnetism might all involve particle-level forces. This vision anticipated later physics, which did unify forces under mathematical field theories. Newton's experimental work in alchemy was methodologically continuous with his optical experiments. Both involved careful observation, controlled manipulation of variables, and systematic record-keeping. He approached alchemical substances with the same empirical rigor he brought to prisms and lenses. The difference lay not in method, but in alchemy's greater theoretical obscurity and symbolic language. Some scholars argue Newton's alchemical work influenced his conception of gravitational force directly. Learning that matter possesses active principles from chemistry could have suggested non-mechanical forces in physics. The philosopher's stone represented matter in its most active, powerful form. Gravitation likewise represented active power pervading all matter universally. Other scholars emphasize discontinuities between Newton's public physics and private alchemy. The Principia's austere mathematical style gives no hint of alchemical concerns or terminology. Newton deliberately excluded alchemical speculations from his published natural philosophy. He maintained strict separation between secure mathematical demonstrations and uncertain chemical theories. Both perspectives capture partial truth about Newton's complex intellectual practice. His mind moved fluidly between mathematical mechanics, optical experiments, chemical operations, and theological studies. He saw connections and analogies where later generations saw separate, unrelated disciplines. The unity existed in Newton's thinking even when not explicit in published texts. The alchemical work remained largely unknown until the 20th century, when manuscripts became accessible. This discovery revolutionized Newton's scholarship by revealing dimensions completely absent from standard histories. The rational, mechanical Newton of Enlightenment mythology gave way to a more complex historical figure. He pursued multiple paths toward understanding nature and divinity simultaneously. Modern chemistry vindicated some alchemical intuitions while rejecting others entirely. Transmutation is possible through nuclear reactions, though not via philosopher's stone. Chemical reactions do involve forces between atoms, though not mechanical collisions alone. Newton's suspicion that active principles govern matter contained genuine insight. His experimental technique influenced subsequent chemistry despite theoretical framework's ultimate failure. Careful, systematic experimentation with detailed record-keeping became standard practice. The search for quantitative laws governing chemical reactions followed Newton's mathematical approach. Later, chemists separated his valid methodology from his invalid theory. Part 7. The Ancient Wisdom Project. Newton believed that ancient civilizations possessed profound knowledge about nature and God that had been lost or corrupted. This was not romantic nostalgia, but a systematic, interpretive framework shaping his entire intellectual program. He spent decades studying ancient texts, comparing mythologies and reconstructing what he called the Prisca Theologia. The ancient theology represented original truths God revealed to Noah and the earliest patriarchs. This framework emerged from Renaissance traditions that Newton inherited and transformed. Scholars like Marsilio Ficino and Giovanni Pico della Mirandola had argued that pagan philosophers possessed partial divine knowledge. They traced connections between Plato, Pythagoras, Hermes Trismegistus, and biblical revelation. Newton adopted this approach, but made it more empirically grounded and historically critical. He believed the original religion consisted of two simple commandments that Christ later reaffirmed. Love God with complete devotion, and love your neighbor as yourself. This pure monotheism descended through Noah, Abraham, Isaac, Jacob, and Moses to the Israelites. But other nations corrupted the original religion into idolatry while preserving fragments of truth. Newton's massive manuscript Theologiae Gentilis Originis Philosophicae reconstructed how this corruption occurred. Ancient priesthoods transformed worship of the one true God into elaborate polytheistic systems. Yet traces of original monotheism persisted in philosophical schools and mystery religions. Pythagoras had learned authentic wisdom during travels in Egypt and Babylon. The Pythagorean system particularly fascinated Newton as encoding genuine natural philosophy in symbolic form. Pythagoras supposedly taught that Earth moves around a central fire, representing the sun. This heliocentric cosmology anticipated Copernicus by 2,000 years, according to Newton's interpretation. Ancient sages understood the true structure of the solar system. Newton analyzed ancient temple architecture as embodying cosmological knowledge deliberately. The Temple of Solomon and pagan temples dedicated to Vesta use circular designs centered on sacred fires. These architectural features symbolize the heliocentric system with the sun as nature's central fire. Worship and natural philosophy were unified in original religious practice. He wrote that one design of the first true religion's institution was proposing the world's frame through temples. Ancient temples served as models, helping people study the cosmos as God's true temple. Religious architecture encoded scientific truth accessible to initiates who understood the symbolism. This explained why ancient wisdom appeared in such obscure allegorical forms. The Prisca Theologia framework also shaped Newton's approach to alchemy and natural philosophy generally. Alchemical texts might preserve ancient chemical knowledge transmitted through symbolic language, protecting it from corruption. Decoding these allegories could recover experimental techniques and theoretical insights. Newton was not discovering new truths, but rediscovering what ancients already knew. This perspective made Newton's work fundamentally restorative rather than revolutionary in his own eyes. He aimed to recover Prisca Sapientia, the ancient wisdom about both natural and divine matters. Modern philosophy had declined from heights achieved by ancient sages and needed restoration. The Principia represented recovery of mathematical natural philosophy that Pythagoras had possessed. Newton's chronological studies attempted to establish accurate timelines for ancient history using astronomical evidence. Ancient texts contained references to celestial events like eclipses and planetary configurations. By calculating when these astronomical phenomena actually occurred, Newton could date historical events precisely. This would reveal the true sequence of ancient civilizations and cultural transmissions. His chronology of ancient kingdoms amended challenged conventional dating of Egyptian and Greek history. Newton argued that standard chronologies exaggerated the antiquity of these civilizations. By correcting these errors, he showed that all ancient wisdom derived ultimately from biblical patriarchs. This vindicated the priority of Hebrew revelation over supposedly older pagan traditions. The project involved detailed analysis of mythological traditions across different cultures seeking common origins. Newton traced how the same basic stories appeared in Greek, Egyptian, and Near Eastern mythology, with variations. These parallels suggested one original source that different cultures preserved and modified. Comparative mythology revealed historical connections between ancient peoples and their knowledge transmission. Newton believed that Phoenician sailors spread ancient wisdom through trade routes connecting civilizations. They transmitted astronomical knowledge, religious concepts, and philosophical ideas across the Mediterranean world. This explained similarities between distant cultures that had no obvious direct contact. Ancient globalization had occurred through maritime trade networks. He also studied how ancient mystery religions preserved esoteric knowledge through initiatory practices. The Eleusinian mysteries and similar cults protected truths from public disclosure through graduated revelation. Initiates learned progressively deeper secrets as they advanced through ritual stages. This hierarchical knowledge system prevented corruption while maintaining authentic traditions. Newton's own practice of concealing important ideas reflected this ancient model. He believed that profound truths should not be cast before those unprepared to receive them properly. The Pythagorean style of hiding deeper meanings in seemingly simple statements became Newton's deliberate strategy. He wrote the general scholium to be understood only by adept readers who could discern hidden significance. This created multiple levels of meaning in Newton's published works, accessible to different audiences. Ordinary readers found mathematical demonstrations and experimental descriptions. Initiated readers recognized theological implications and connections to ancient wisdom traditions. Newton communicated simultaneously with multiple audiences through carefully crafted ambiguity. The Prisca Theologia framework connected Newton's natural philosophy to his anti-Trinitarian theology directly. The original religion was pure monotheism, before 4th century corruption introduced Trinitarian errors. Similarly, the original natural philosophy understood mathematical laws and heliocentric cosmos before medieval decline. Both needed restoration to their pristine forms through critical scholarship and empirical investigation. Newton saw himself as living through a period of prophesied restoration, approaching gradually. The Protestant Reformation had begun recovering true religion, but remained incomplete. His own work in natural philosophy contributed to broader reformation, restoring ancient wisdom. Science and theology both participated in God's plan for revealing truth to humanity. This vision shaped Newton's understanding of his historical role and intellectual mission. He was not a modern revolutionary breaking with tradition, but a restorer recovering lost knowledge. The ancients had known essential truths that subsequent generations corrupted or forgot. Newton's task was recovering and purifying this wisdom for transmission to future generations. Modern scholars debate how seriously to take Newton's Prisca Theologia framework. Some view it as peripheral hobby disconnected from his serious scientific work. Others argue it fundamentally shaped his motivations and interpretive strategies throughout his investigations. The evidence suggests it was indeed central to Newton's self-understanding and intellectual identity. The framework also reflected broader cultural assumptions of Newton's era about knowledge and history. Many 17th century thinkers believed human learning had declined since ancient times. Progress meant recovering lost wisdom rather than discovering entirely new truths. Newton's Prisca Theologia was an intellectually respectable position within his context. Yet Newton pursued this project with unusual intensity and systematic rigour compared to contemporaries. His chronological calculations and mythological comparisons went far beyond casual antiquarian interest. He devoted decades to reconstructing ancient wisdom traditions with the same energy he brought to physics. This was core business, not peripheral curiosity for Newton. Part 8. Impact and Legacy. Newton's ideas transformed philosophy as profoundly as they revolutionized physics and mathematics. Every major Enlightenment thinker from the 1700s grappled with implications of his work. His methodology, metaphysics, and mathematical achievements set agendas for philosophy throughout the 18th century. Understanding this period requires recognizing Newton's philosophical centrality, not just his scientific importance. John Locke knew Newton personally, and their philosophical positions influenced each other significantly. Locke's empiricism emphasized sensory experience as knowledge's foundation, rejecting Cartesian innate ideas. This aligned with Newton's experimental philosophy and skepticism toward purely rationalist metaphysics. Both insisted that careful observation must constrain theoretical speculation. Yet Locke also recognized limits to what sensory experience alone could establish about nature. He distinguished primary qualities like extension and motion from secondary qualities like color and taste. Primary qualities belong to objects themselves, while secondary qualities depend on perception. This framework tried to reconcile mathematical natural philosophy with empiricist epistemology. Newton influenced Locke's thinking about space, substance, and our knowledge of material reality. Locke struggled with whether space is substance, property, or pure relation. Newton's absolute space conception offered one solution, though Locke never fully endorsed it. Their correspondence reveals ongoing dialogue about fundamental metaphysical and epistemological questions. George Berkeley developed idealist philosophy partly in response to Newtonian mechanics and Lockean empiricism. Berkeley rejected material substance, entirely arguing that only minds and ideas exist. Physical objects are collections of sensory ideas perceived by minds. This radical move eliminated the gap between appearance and reality that troubled Locke. Berkeley also attacked Newton's absolute space and calculus on philosophical and mathematical grounds. He argued that absolute space existing independently of perception made no empirical sense. The calculus relied on incoherent notions of infinitesimal quantities that were neither something nor nothing. These critiques exposed genuine tensions in Newton's foundations, though without displacing his system's success. David Hume pursued the most systematic attempt to apply Newtonian method to human nature and morality. His Treatise of Human Nature carried the subtitle, An Attempt to Introduce Experimental Method into Moral Subjects. Hume meant to do for psychology and ethics what Newton achieved for physics. This required finding empirical regularities in human mental life and inferring general principles explaining them. Hume's analysis of causation directly engaged Newton's methodology and its philosophical foundations. Newton claimed to deduce gravity's existence from phenomena using induction. But Hume argued that induction itself has no rational justification beyond custom and habit. We cannot demonstrate that unobserved cases will resemble observed ones. Causation reduces to constant conjunction of events in our experience according to Hume's radical analysis. We observe that certain types of events regularly follow others and form expectations accordingly. But we never perceive necessary connections between causes and effects directly. The idea of causal power or force is a psychological projection, not an empirical discovery. This skeptical argument threatened to undermine the entire Newtonian enterprise philosophically. If induction lacks rational foundation, then Newton's inferences from phenomena become unjustifiable. The laws of motion and gravitation have no more certainty than habitual expectations. Hume's analysis created what Kant later called the crisis waking him from dogmatic slumbers. Yet Hume himself remained deeply impressed by Newton's achievement and did not intend to discredit it. He distinguished between practical certainty sufficient for life and science versus absolute philosophical certainty. Newton's method works effectively even if its ultimate justification remains philosophically obscure. We can use induction reliably while acknowledging we cannot fully explain why it succeeds. Continental philosophers engaged Newton's work differently than British empiricists. Voltaire became Newton's greatest popularizer in France during the 1730s and 40s. His Elements of Newton's philosophy presented the Principia and Optics for educated readers without advanced mathematics. Voltaire championed Newton as exemplifying reason's power against religious superstition and philosophical dogmatism. Émilie du Châtelet produced the definitive French translation of the Principia that remains standard today. She was a brilliant mathematician who understood Newton's work deeply, both technically and philosophically. Her commentary clarified difficult passages and connected Newtonian physics to Leibnizian metaphysics. Du Châtelet showed how to synthesize insights from competing philosophical traditions. The Leibniz-Clark correspondence from 1715 to 16 became philosophically crucial for subsequent debates. Leibniz attacked Newton's absolute space as violating the principle of sufficient reason. Samuel Clarke defended Newton while articulating connections between space, God's omnipresence, and divine action. The exchange crystallized fundamental disagreements between rationalist and empiricist approaches. These debates remained vital throughout the 18th century, influencing thinkers across Europe. They shaped Kant's development during the 1770s as he wrestled with space, time, and causation. Kant recognized that both rationalist metaphysics and empiricist skepticism faced fatal difficulties. Neither could adequately explain how Newtonian science achieves synthetic knowledge about nature. Kant's critical philosophy attempted to transcend the rationalist-empiricist dichotomy that Newton embodied uncomfortably. Space and time are neither objective features of things themselves nor merely empirical relations. Instead, they are pure forms of sensory intuition structuring all possible experience. This makes them both necessary and yet not features of reality, independent of human cognition. Kant argued that Newton's laws hold with necessity because they reflect how our minds must structure experience. Causation is not discovered empirically, as Hume claimed, nor deduced from pure reason, as rationalists held. Rather, causation is a category our understanding imposes, making objective experience possible at all. This explained both Newton's success and the limits of what physics can reveal about ultimate reality. The Kantian reinterpretation of Newton dominated German philosophy through the 19th century. It separated Newton's physics from his metaphysical commitments about absolute space and divine action. The mathematical laws could be retained while rejecting Newton's theological and metaphysical framework. This separation enabled the secular scientific worldview that emerged during the 1800s. Meanwhile, Practical science proceeded by extending Newton's methods to new domains. Lagrange and Laplace developed analytical mechanics, reformulating Newtonian physics with new mathematical techniques. They achieved spectacular successes predicting planetary motions with unprecedented precision. Laplace famously claimed that his celestial mechanics needed no hypothesis about God. This secularization inverted Newton's intentions completely, since he saw physics as revealing divine action. The Enlightenment appropriated Newton as patron saint of rational secular inquiry. They suppressed or ignored his theology, alchemy, and prophecy studies, focusing exclusively on mathematical physics. The Newton they celebrated was a mythological construct bearing limited resemblance to the historical person. The 19th century saw Newton's mechanics extended to electromagnetism, thermodynamics, and statistical physics. Maxwell's equations governing electromagnetic fields followed Newtonian methods of mathematical generalization from experiments. The kinetic theory of gases applied Newtonian mechanics to molecular motion, explaining thermodynamic phenomena. Every successful physical theory adopted Newton's framework, combining mathematics with empirical constraint. Yet anomalies accumulated that Newtonian physics could not explain adequately. The orbit of Mercury showed discrepancies with gravitational predictions. The speed of light appeared constant in all reference frames, contradicting Newtonian relativity. Atomic phenomena required discontinuous energy levels impossible in classical mechanics. Einstein's relativity theories in 1905 and 1915 displaced Newtonian mechanics fundamentally. Space and time are not absolute, but relative to reference frames and interwoven into space-time. Gravity is not force, but space-time curvature caused by mass and energy. These revisions overturn Newton's basic framework while preserving his laws as excellent approximations. Quantum mechanics beginning in the 1920s undermined Newtonian determinism even more radically. Physical processes at atomic scales involve irreducible randomness, not just ignorance of initial conditions. Particles do not have definite positions, and momenta simultaneously contrary to classical assumptions. The mathematical framework of quantum theory bears little resemblance to Newtonian mechanics. Yet Newton's broader methodological legacy persisted through these revolutionary transformations. Physics still combines mathematical theory with experimental test following Newton's model. Laws are formulated as differential equations constraining possible behaviors. Theories succeed by making precise predictions that observation can confirm or falsify. Philosophy of science continues debating issues Newton's work raised about confirmation and theoretical underdetermination. How do observations constrain theory choice when multiple theories can fit the same data? What distinguishes legitimate scientific hypotheses from unfalsifiable metaphysical speculation? Newton's hypotheses non-fingo remains relevant to contemporary debates about scientific realism and methodology. Part 9. The Contradictions and Limits. Newton's system contained profound tensions that he never fully resolved and that subsequent science exposed. His methodological declarations emphasized deriving conclusions from phenomena without feigning hypotheses. Yet his fundamental framework relied on metaphysical commitments about absolute space impossible to observe directly. This gap between empiricist rhetoric and rationalist practice troubled critics from the beginning. The absolute space doctrine was necessary for Newton's physics to work as he formulated it. Laws of motion require distinguishing true acceleration from merely apparent changes in relative position. Without absolute motion, the second law becomes empirically empty, since all motion is relative to reference frame. Yet Newton explicitly acknowledged that absolute space and time cannot be measured directly. He tried to resolve this by arguing that forces provide empirical access to absolute acceleration. True changes in motion result from forces impressed upon bodies. We can detect forces through their observable effects, like tension in rotating buckets water. But this argument is circular, since identifying forces already presupposes distinguishing real from apparent motion. The bucket experiment was meant to demonstrate absolute rotation independent of external reference bodies. When the bucket spins, the water eventually rotates with it and climbs the sides, forming a concave surface. Newton argued this shows genuine rotation, since the shape change occurs even when water moves with bucket. The rotation must be relative to space itself, not to surrounding material bodies. Ernst Mach criticized this reasoning in the late 1800s, pointing to alternative interpretations. Perhaps the water's shape responds to rotation relative to distant masses throughout the universe. If all the stars rotated around a stationary bucket, the same effect might occur. This undermined Newton's claim to have demonstrated absolute motion empirically. Einstein's general relativity ultimately vindicated Mach's intuition, showing that inertial effects depend on matter distribution. Mass curves space-time, and this curvature determines inertial reference frames locally. The distinction between inertial and non-inertial motion remains, but is dynamical, not absolute. Space does not exist independently with fixed structure determining what counts as acceleration. Newton's gravity theory faced the action at a distance problem that Cartesians and Leibnizians emphasized relentlessly. How can the Sun exert force on Earth across 93 million miles of empty space? Mechanical philosophy demanded contact between bodies for causal interaction. Gravitational attraction violated this principle, seeming to invoke occult sympathies medieval philosophy had abandoned. Newton recognized this difficulty, but insisted that mathematical demonstration of gravity's existence and law trumped mechanical scruples. He speculated privately about ether mediums that might transmit gravitational effects mechanically. But he refused to publish such speculations, lacking experimental support. Better to acknowledge ignorance about mechanism than to feign explanations without empirical foundation. This methodological stance was philosophically bold, but left Newton vulnerable to charges of inconsistency. He demanded mechanical explanations from others while exempting his own central force from the requirement. Leibniz and Huygens argued that vortex theories at least propose mechanisms, even if details remained speculative. Newton's approach seemed to abandon the goal of genuine physical explanation entirely. Later, physics vindicated Newton's willingness to accept mathematically precise forces without mechanical reduction. Electromagnetic forces operate similarly through empty space without material medium. Quantum field theory describes forces through field equations, not mechanical particle collisions. The demand for mechanical explanation proved too restrictive for fundamental physics. Yet modern forces differ fundamentally from Newtonian gravity in crucial ways that Newton could not anticipate. They propagate at finite speed, not instantaneously across all distances. Changes in source masses take time to affect distant bodies travelling at light speed through space-time. Newton's instantaneous action at a distance was not just unexplained, but empirically incorrect. The corpuscular theory of light illustrates another major limitation in Newton's physics. He marshalled impressive arguments for light consisting of particles rather than waves. Light travels in straight lines, producing sharp shadows, unlike sound that diffracts around obstacles. Reflection resembles elastic collision of particles bouncing off surfaces. But Newton's theory could not adequately explain phenomena like colours in thin films. Why does light sometimes reflect and sometimes transmit through soap bubbles unpredictably? Newton proposed fits disposing corpuscles alternately toward reflection or transmission. These fits required wave-like properties grafted onto particle foundations awkwardly. Young's double-slit experiment in 1801 provided devastating evidence against corpuscular theory. Interference patterns with alternating bright and dark bands clearly demonstrated wave behavior. Particles travelling through two slits could not produce such patterns. By mid-1800s, wave theory dominated optics completely. Then the photoelectric effect, discovered around 1900, resurrected particle concepts unexpectedly. Light ejects electrons from metals in ways wave theory cannot explain properly. Einstein showed that treating light as discrete energy packets explained observations perfectly. The modern photon concept vindicated aspects of Newton's intuition, despite his theory being wrong. Wave-particle duality ultimately transcended both classical pictures, showing that neither particles nor waves adequately describe quantum entities. Light exhibits both wave and particle properties depending on experimental context. Newton and Huygens were both partially correct and both fundamentally wrong. Nature's behavior at quantum scales defies classical concepts entirely. Newton's methodology created tensions between inductive caution and theoretical boldness. He claimed to derive conclusions from phenomena using induction without hypothetical speculation. Yet universal gravitation extended far beyond observable evidence in dramatic theoretical leaps. He had only tested objects on Earth and visible celestial bodies. Extrapolating to all matter everywhere throughout infinite space involved enormous theoretical risks. Countless potential exceptions or limitations could exist beyond experimental reach. Newton's rule 3 justified this universalization, but the rule itself was not derived from phenomena. It was a methodological principle assumed to make natural philosophy possible. David Hume's critique of induction exposed this vulnerability systematically. No amount of observed constant conjunction proves that future cases must resemble past ones necessarily. We cannot demonstrate inductively that induction works, since that argument begs the question. Newton's confident generalizations from limited evidence lacked the certainty he claimed. The problem of induction remains philosophically unsolved despite practical scientific success. We continue using inductive inference because it works, not because we can justify it rationally. Newton's methodology succeeded spectacularly, but its logical foundations remained insecure. This gap between practical success and philosophical justification persists in contemporary science. Newton's theological framework also created tensions with his public natural philosophy. He believed God acts continuously in the world, maintaining cosmic order through providential intervention. Yet his published physics treated nature as governed by mathematical laws operating mechanically. How divine action relates to natural law remained unresolved. If God must occasionally adjust planetary orbits to maintain stability, then natural laws alone do not suffice. This suggests the creation is imperfect, requiring divine correction, as Leibniz charged. But if laws govern completely, then God's role reduces to initial creation, as deists argued. Newton wanted active divine governance without undermining natural law's autonomy. His heretical theology created additional complications that he concealed from public view. The general scholium's theological statements carry Arian implications detectable only to those familiar with the debates. Newton was simultaneously making physics accessible to all while encoding heretical theology for adepts. This duplicity reflected his impossible situation, caught between intellectual honesty and survival necessity. The suppression of Newton's theological and alchemical manuscripts created a distorted legacy. Enlightenment thinkers celebrated him as embodying pure, rational scientific inquiry, free from religious prejudice. The real Newton devoted more energy to theology and alchemy than to physics. His unified vision, combining all these domains, was fractured into separate, incompatible parts. Modern physics has abandoned most of Newton's specific physical doctrines while retaining methodological insights. Absolute space and time are gone, replaced by relativistic space-time. Gravitational force is gone, replaced by space-time curvature. Deterministic trajectories are gone, replaced by quantum probability amplitudes. Yet the mathematical physics Newton pioneered continues as the foundation of all physical science. The idea that nature follows precise mathematical laws remains central despite revolutionary theory changes. Deriving predictions from theory and testing them experimentally defines scientific practice today. Newton established these standards even though his specific theories proved limited. Part 10. The Unified Vision. Understanding. Newton requires grasping how seemingly disparate pursuits formed a coherent whole in his mind. Modern disciplinary boundaries between physics, theology, alchemy and history did not exist for him. All these investigations aimed at the same ultimate goal, revealing God's nature and will through creation. Natural philosophy, biblical exegesis and alchemical experiments were different methods pursuing unified truth. Newton believed that God left traces of divine wisdom in multiple books requiring different reading methods. The Book of Nature reveals God's power and intelligence through mathematical laws and orderly phenomena. The Book of Scripture reveals God's will and plan for humanity through prophetic and historical texts. Ancient philosophical and alchemical texts preserve corrupted fragments of original revelation. All three sources ultimately converge on the same truths when properly interpreted and purified. Natural philosophy discovers mathematical laws governing motion and force. Theology recovers pure monotheism, underlying corrupted Trinitarian doctrines. Alchemy reveals active principles governing matter's transformations beyond mechanical interactions. The Prisca Sapientia framework unified these domains by showing they all derive from original divine revelation. God revealed both natural and moral truths to Noah and the patriarchs. Their descendants transmitted this wisdom through various cultural traditions, preserving it imperfectly. Newton's task was recovering and purifying these traditions to restore original unified knowledge. His anti-Trinitarian theology was not incidental, but central to this entire vision. The Trinity represented the same kind of corruption that affected natural philosophy during medieval decline. Just as scholastic Aristotelianism obscured mathematical laws of nature, Trinitarian metaphysics obscured simple monotheistic truth. Both needed reformation through return to original sources purged of later accretions. Newton's conception of God as absolutely one and omnipresent shaped his physics fundamentally. Divine omnipresence means God exists everywhere, constituting space itself through his eternal presence. This makes space more like divine attribute than physical container. The unity and continuity of space reflects God's unity and indivisibility. Similarly, time's absolute flow represents God's eternal duration, ordering all events. Past, present, and future exist for God simultaneously in eternal now. But creatures experience time as succession of moments flowing irreversibly. Absolute time provides the framework in which all change and motion occur. Gravity itself might be direct divine action rather than mechanical force transmitted through matter. God's will maintains the cosmos by exerting attractive forces between all material bodies universally. The mathematical inverse square law describes how God chooses to govern planetary motions. Natural law is divine will, made manifest through regular, predictable action. This explains Newton's confidence that mathematical laws will prove universal despite limited observational evidence. God's nature as rational and consistent ensures that divine action follows uniform principles everywhere. The same laws operate throughout infinite space because one God governs all creation. Mathematical natural philosophy reveals divine rationality imprinted on physical reality. Newton's alchemy sought active principles that would complete the mechanical philosophy's inadequate framework. Pure mechanism treating matter as passive and inert could not explain chemical affinity or vital processes. But matter infused with active principles directing selective combinations could accomplish what mechanisms alone could not. These principles might be God's ongoing creative activity operating at microscopic scales. The philosopher's stone represented matter in its most active, perfected state, embodying maximal divine virtue. Transmutation would be possible by imparting these active principles to base metals, transforming their essential natures. This was not magic, but natural philosophy extended to domains where mechanical explanations failed. Alchemy investigated aspects of divine action in matter complementing mathematical physics. Newton's biblical prophecy studies fit into this framework by revealing God's plan for history's unfolding. Daniel and Revelation encrypted the timeline of true religion's corruption and eventual restoration. Understanding these prophecies showed where human history stands in divine providence. Newton calculated he lived during the long-predicted apostasy before final reformation. His chronological studies established accurate timelines showing how ancient wisdom traditions developed and interacted. This historical work was not antiquarian curiosity, but essential for understanding knowledge transmission. Tracing how Egyptians, Greeks and Hebrews shared and corrupted original revelation illuminated which traditions preserved authentic truth. History revealed the degradation Newton aimed to reverse through his restorative project. The methodological unity underlying all these investigations centered on careful observation and textual criticism. Whether examining prisms, studying manuscripts, or conducting chemical experiments, Newton applied rigorous empirical methods. He weighed evidence critically, compared sources systematically, and drew conclusions cautiously. The same intellectual virtues govern natural philosophy and biblical scholarship. Newton's experimentalism in physics extended to his theological method, treating scripture as observational data. He compared manuscript variants, noting discrepancies and later additions, like a natural historian classifying specimens. Textual criticism identified corruptions, distinguishing authentic revelation from human interpolations. This empirical approach to theology scandalized those treating Scripture as uniformly inspired. Similarly, his alchemy involved systematic experimentation, recording results and modifying procedures based on observations. He did not accept alchemical authorities uncritically, but tested claims through laboratory work. This experimental attitude unified his approach across domains where others saw fundamentally different kinds of inquiry. For Newton, knowledge always required empirical grounding regardless of subject matter. The mathematical dimension also unified Newton's various investigations, though less obviously than experimental method. Natural philosophy employed mathematics explicitly in laws of motion and gravitational theory. But chronology also used mathematical calculation, determining dates from astronomical references. Even prophecy interpretation involved numerical patterns and temporal calculations. Newton saw mathematics as reflecting divine reason ordering creation according to rational principles. The mathematical harmony of planetary motions reveals God's aesthetic and rational perfection. Ancient sages recognized this, which explains why Pythagoras emphasized mathematical relationships in philosophy. Mathematics provides privileged access to divine wisdom underlying all phenomena. The unified vision explains Newton's extraordinary motivation and productivity across multiple demanding domains. He was not dilettante, dabbling in unrelated hobbies, but pursuing one comprehensive goal with total commitment. Every investigation contributed to understanding God's nature and recovering original divine revelation. This gave his work existential urgency and personal meaning beyond mere intellectual curiosity. It also explains the secrecy surrounding much of his work. Revealing heretical theology would destroy his ability to continue the mission. Publishing incomplete alchemical speculations would expose sacred knowledge to corruption or ridicule. Newton concealed what he judged unsuited for public disclosure while publishing what would advance collective understanding. The tragedy is that this unified vision could not survive Newton's death intact. His executors suppressed theological and alchemical manuscripts, protecting his reputation. Enlightenment appropriated Newton as secular rationalist, rejecting the very theological framework driving his work. The sanitized Newton bore little resemblance to the historical figure. Modern Newton scholarship has painstakingly reconstructed the unified vision from manuscript evidence. We now understand that physics, theology, and alchemy formed an integrated intellectual system for Newton. This recognition transforms how we interpret his published works, revealing layers of meaning invisible before. The general scholium's theological statements are not afterthoughts, but express core convictions motivating the entire Principia. Yet we cannot fully recover Newton's perspective because our intellectual world differs fundamentally from his. We assume science and religion occupy separate, non-overlapping magisteria. We distinguish empirical investigation from metaphysical speculation more sharply than Newton did. Our disciplinary divisions prevent seeing the connections that Newton considered obvious. The unified vision also contained genuine tensions and contradictions Newton could not fully resolve. How divine action relates to natural law remained conceptually problematic. Whether matter possesses inherent active principles or depends entirely on divine will was unclear. The relationship between mathematical description and physical explanation generated ongoing confusion. These tensions prove productive, forcing subsequent thinkers to address fundamental questions about scientific explanation. Does physics aim to describe how nature behaves mathematically, or to explain why it behaves that way? Can we separate empirical science from metaphysical commitments about reality's ultimate nature? Newton's work raised these issues unavoidably, requiring philosophical clarification. His legacy is therefore both scientific and philosophical, shaping how we conceive inquiry itself. The mathematical physics Newton created became the model for all exact science. But the philosophical tensions his work exposed continue driving debates about scientific method and realism. We still struggle with problems Newton identified even after abandoning his specific solutions. Understanding Newton whole, integrating his public physics with private theology and alchemy, reveals a mind of staggering range and depth. He mastered mathematics, physics, astronomy, optics, theology, history, chronology, and chemistry at the highest levels. More remarkably, he saw profound connections between these domains where others saw only separation. This synthetic vision animated everything he achieved. The unified Newton challenges our assumptions about how great minds work and what drives scientific revolution. We imagine pure rational inquiry free from religious and metaphysical commitments. Newton shows that the actual history is far more complex, with religious conviction and scientific method intertwined. His heretical theology and alchemical investigations were not obstacles to his physics, but integral parts of a comprehensive quest for truth.